Good day, everyone. Today we'll tackle about factor analysis. Factor analysis is a data reduction technique designed to represent a wide range of attributes on a smaller number of dimensions. Factor analysis is defined as a statistical approach that can be used to analyze interrelationship among a large number of variables and explain these variables in terms of their common underlying dimension or factor. Variables are not classified as either dependent or independent. Instead, the whole set of interdependent relationship among variables is examined in order to define a set of common dimensions called factors. There are two types of factor analysis. First is exploratory factor analysis. Exploratory factor analysis summarizes data by grouping correlated variables, investigating sets of measured variables related theoretical constructs, and usually done near the onset of research. The second type is confirmatory factor analysis. Confirmatory factor analysis is more advanced technique when factor structure is known or at least theorized. Testing generalization of factor structure to new data. There are 6 stages of factor analysis decision process. In the first stage, objective. In data summarization, definition of its structure is done. Next is data reduction. Here, the purpose is to retain the nature and character of original variables but reduce their numbers to simplify the subsequent multivariate analysis. In stage 2, designing factor analysis, there are two types of factor analysis. The first one is R-type, which is used in traditional correlation matrix. The second is Q-type factor analysis. Here, there would be a factor matrix that would identify similar individuals. Stage 3, assumptions. The first assumption is models are usually based on linear relationships. Models assumes that the data collected are interval scaled. Multicollinearity in the data is desirable because the objective is to identify interrelated sets of variables. The data should be amenable for the factor analysis. It should not be such that a variable is only correlated with itself and no correlation exists with any other variables. Another method of determining appropriateness of factor analysis is Bartlett test of sphericity, which provides statistical significance that correlation matrix has significant correlation among at least some variables. Stage 4, deriving factors and assessing overall fit. An exact quantitative base for deciding number of factors to extract has not been developed. That is why there are different stopping criteria to be followed. One is latent truth criteria. Each variable contributes a value of 1 to the total eigenvalues. This method is suitable when number of variables is between 20 and 50. Number 2, a priori criterion. Researcher already knows how many factors to extract. Thus, researcher instruct the computer to stop analysis when specified number of factors have been extracted. Number 3 is percentage of variance criterion. This approach is based on achieving a specified cumulative percentage of total variance extracted by successive factors. Number 4 is discrete criterion. The proportion of unique variance is substantially higher in the later variables. The discrete test is used to identify the optimum number of factors to be extracted before the amount of unique variance. As a general rule, discrete test results in at least 1 and sometimes 2 or more factors being extracted than does latent truth criteria. There are 3 processes in interpreting the factors. 1 is estimate the factor matrix. An initial annotated factor matrix is computed containing factor loading. Higher loading indicates that variable is representative of factor. They achieve objective of data reduction only. Number 2 is factor rotation. As unrotated factor don't provide the required information that provide adequate interpretation of data. Thus, we need the rotational method to achieve simpler factor solutions. Ultimate effects of rotation is to redistribute the variance from earlier factors to later ones. There are two methods of factor rotation. First is orthogonal factor rotation, and second is oblique factor rotation. Major orthogonal factor rotation approaches include: number 1 is Quartimax. Its goal is to simplify the rows of factor matrix. Number 2 is Varimax. Its goal is to simplify the columns of factor matrix. It maximizes the sum of variance of required loading of factor matrix. 3 is Equimax. Equimax compromise between quanti and vari. It hasn't gained wider acceptance. Validation of factor analysis. Validation of factor analysis is assessing the degree of generalizability of results to population and potential influences of case on the overall result.
Now let's run a factor analysis in SPSS. Here is an example. In the SPSS menu bar, click Analyze. Then point to Dimension Reduction, click Factor. Next, select the items 13 to 24 as variables. Under the descriptives, click the univariate descriptives. Then determinant, KMO, and reproduce. Then click Continue. Under the extraction, the method is principal axis factoring. Then click the scree plot. Then in the fixed number of factors, we have 3. Then click Continue. Under the rotation, click the Varimax. Then the loading plots. Then click Continue. Under the scores, click the Display Factor Score Coefficient matrix. Then continue. Under the options, suppress the small coefficients, and the absolute value is 0.3. Then click Continue. Then, OK. So here are the outputs. The table above shows the output of univariate option and the print subcommand. These are the means of the variables used in the factor analysis. These are the standard deviations of the variables used in the factor analysis. Analysis N. This is the number of cases used in the factor analysis. Next we have is the correlation matrix. All we want to see in this table is that the determinant is not 0. If the determinant is 0, then there will be computational problems with the factor analysis. KMO and Barrett's test. KMO or Kaiser-Meyer-Alkin measure of sampling adequacy. This measure varies between 0 and 1, and values closer to 1 are better. A value of 0.6 is suggested minimum. Barrett's test of sphericity. This tests the null hypothesis that the correlation matrix is an identity matrix. An identity matrix is a matrix in which all of the diagonal elements are 1 and all of the diagonal elements are 0. You want to reject this null hypothesis. Taken together, these tests provide a minimum standard which should be passed before a factor analysis should be conducted. Communalities. This is the proportion of each variable's variance that can be explained by the factors. It is also noted as h squared and can be defined as the sum of squared factor loadings for the variables. Initial. With principal factor axis factoring, the initial values on the diagonal of the correlation matrix are determined by the squared multiple correlation of the variable with the other variables. For example, if you regress items 14 through 24 on items 13, the squared multiple correlation coefficient will be 0.564. Extraction. The values in this column indicate the proportion of each variable's variance that can be explained by the retained factors. Variables with high values are well represented in the common factor space, while variables with low values are not well represented. They are reproduced variances from the factors that you have extracted. Total variances. Factor. The initial number of factors is the same as the number of variables used in the factor analysis. However, not all 12 factors will be retained. Initial int values. Int values are the variances of the factors. Because we conducted our factor analysis on the correlation matrix, the variables are standardized, which means that each variable has a variance of 1, and the total variance is equal to the number of variables used in the analysis, in this case, 12. Total. This column consists the equivalence values. The first factor will always account for the most variance, and the next factor will account for as much of the leftover variance as it can, and so on. Percentage of variance. This column contains the percent of total variance accounted for by each factor. Cumulative percentage. This column contains the cumulative percentage of variance accounted for by the current and all preceding factors. Extraction sums of squared loadings. The sum of rows in this panel of the table correspond to the number of factors retained. The values in this panel of the table are calculated in the same way as the values in the left panel, except that here the values based on the common variance. The values in this panel of the table will always be lower than the values in the left panel of the table because they are based on the common variances, which is always smaller than the total variances. Rotation sums of squared loadings. The values in this panel of the table represents the distribution of the variance after the Varimax rotation. Varimax rotation tries to maximize the variance of each of the factors so that the total amount of variance accounted for is distributed over 3 extracted factors. Scree plot. The scree plot graphs the int value against the factor number. You can see these values in the first two columns of the table immediately above. From the third factor on, you can see that the line is almost flat, meaning each successive factor is accounting for smaller and smaller amounts of the total variances. Factor matrix. This table contains unrotated factor loadings, which are correlations between the variables and the factor. Because these are correlations, possible values range from -1 to +1. On the format subcommand, we use the option .3, which tells Spss not to print any of the correlations that are less than 0.3. Factor. The columns under his heading are the unrotated factors that have been extracted. As you can see by the footnote provided by the Spss, 3 factors were extracted. Reproduced correlation. The reproduced correlation matrix is the correlation matrix based on the extracted factors. You want the values in the reproduced matrix to be as close to the values in the original correlation matrix as possible. If the reproduced matrix is very similar to the original correlation matrix, then you know that the factors that were extracted accounted for a great deal of the variances in the original correlation matrix, and these few factors do a good job on representing the original data. Residual. As noted in the first footnote provided by Spss, the values in this part of the table represent the differences between the original correlations and the reproduced correlations which are shown in the top part of this table. Rotated factor matrix. This table contains the rotated factor loadings, which represent both the variables are weighted for each factor, but also the correlation between the variables and the factor. Because these are correlations, possible values range from -1 to +1. On the format subcommanded, we use the option blank .3, which tells the Spss not to print any of the correlations that are less than 0.3. Factor transformation matrix. This is the matrix by which you multiply the unrotated factor matrix to get the rotated factor matrix. Factor plot. The plot above shows the items in the rotated factor space. While this picture may not be particularly helpful, when you get this graph in the Spss output, you can interactively rotate it. This may help you to see how the items are organized in the common factor space. Factor score coefficient matrix. This is the factor weight matrix and is used to compute the factor scores. Factor score covariances matrix. Because we use an orthogonal rotation, this should be a diagonal matrix, meaning that the same number should appear in all three places along the diagonal. In actuality, the factors are unrelated. However, because factor scores are estimated, there will be slight correlations among the factor stars.